I am pleased to introduce to you Dr. Beatriz Villarroel. She is a project leader of the Vanishing and Appearing Sources During a Century of Observations, VASCO for short, where she is searching for vanishing stars and other anomalies in the sky. She received her PhD in astronomy from Uppsala University in 2017. She is currently an international postdoctoral researcher, sharing her time between Nordita and AIC Tenerife in Spain. In March 2021, she received the L'Oreal UNESCO for Women in Science Prize in Sweden for her search for vanishing stars. Welcome to the symposium, Beatrice.
Thank you.
I'm excited to hear you speak. Please go ahead.
My pleasure. So I'm going to tell you about why we should search for astronomical anomalies, and I will also tell you about the VASCO project. But I think we should start with the history of astronomy. So, I don't know how many of you have heard about quasars. So quasars are like the most luminous objects you have in the universe. And here you see a number of pictures of typical quasars, where you can see something very, very luminous, very often so that it like oversaturates the image. And when one first discovered it in 1963, one had no clue what it was. One saw actually something that looked really anomalous. So this was the first object that one saw, and the discoverer Martin Schmidt, he saw a star that had a very, very peculiar spectrum. Because this spectrum, it wasn't the spectrum of a normal star. It was it was redshifted. The light was stretched so that it looked like it was super, super far away, like a galaxy is usually having a redshift. And so when Martin Schmidt saw it, he was like wondering, what is it? It looks like a star, but the spectrum is of a galaxy, and it had very strong emission lines as well. So that was the discovery of the first quasar. Today we know that these are no anomalous objects, even if they looked like something anomalous in 1963. And rather so that we know today that all galaxies have been a quasar at some point, at some stage in their life. So what is a quasar? Well, each galaxy has a supermassive black hole in its center, and when you have a very hot gas falling upon this supermassive black hole, you get lots of photon production, and you produce all this super strong emitting light, super strong light in the center of the galaxy. And for example, a quasar can emit from this little region just in the absolute center of the galaxy. That is, I mean, it's region that is no larger than, let's say, like a solar system. It can emit thousands times more light than the whole Milky Way stars can emit together. So these are very powerful things. So today we know that there are like not only quasars, there are other type of active galactic nuclei, which are the same family of objects. But it looked like an anomaly when it first was discovered. And in this way, anomalies in astronomy have always slowly pushed science to progress. Sometimes it not always pushed science to progress. Let's take another example. In the 70s and in the 80s, one discovered more anomalies, and anomalies related to quasars and active galactic galaxies. Active galactic nuclei. For example, this one is a pair of galaxies that are bridged here by gas, or it looks like they're bridged. And so what's unusual about this pair of objects? Well, redshift is a measure of distance. So the larger the redshift, the greater the distance to the object. And you can see here in this image that actually the two galaxies are residing on completely different redshift, something that is completely destroying the idea of the expanding universe. This was discovered by Halton Arp, and he found hundreds more examples of these redshift anomalies. And when it was found in the 80s, this became a huge controversy, because there were some scientists like Halton Arp himself and Barbridge and Fred Hoyle, some famous scientists that believed that this was disproving the whole expanding universe idea, while others were saying no, but look, this could be just a projection effect, that you have something, they are at different redshifts, and then it looks like they are in a pair of objects. And so this controversy went on because Halton Arp and colleagues, they were finding that you had a much more concentration of background and foreground objects near quasars, so that also had like very strong radio emission. And this discussion went on for another 10 years until people got tired of arguing about it, and they just assumed that, no, this is all wrong and anomalous redshifts are wrong, and they simply abandoned it. It's an example of that not every anomaly is going to push science forward. Sometimes it might be abandoned before it's even resolved. Like in this case, we actually don't have a solution to it, and we are not sure that one could have just ignored it, but this is what we assume. And when people were seeing, like, when the Halton Arps gang et al. Were seeing pairs of galaxies and so on, they were imagining them like splitting objects, while today we think that they are actually gravitationally falling upon each other and merging. So anomalies have also emerged from when we have been looking for ET. So historically, it has been very interesting for people to look for ET, extraterrestrial intelligence, in the radio, because we are emitting in the radio, so thus we also hope that someone else might emit in the radio, and we maybe can detect that civilization. It was proposed the first time in 1959 in the Nature journal. That was in the times when you could actually publish about ET in the Nature journals. Later it became slightly more difficult. And it was based on a proposal of Cocconi and Philip Morrison. So if you actually would detect something ET in the radio, you would have a clear signal of communication. There wouldn't be no mistakes. However, it's a little bit difficult because you need to follow each and every star over tens of years and work on it very carefully sometimes. And there are actually big projects now happening, searching for ET in the radio. And if you're interested in that, then the Breakthrough Listen has many papers on how they are looking for them. So far, they haven't found anything. But this is the search space that people who are interested, or astronomers who are interested in ET, usually use. Anyway, many astronomers do radio astronomy without looking for ET. And here is one example of Jocelyn Bell. In 1967, she was a student, and she had just helped to complete our radio telescope, or complete the building of it. And she was working with her master's thesis advisor, Anthony Hewish. And right after that, they just started this radio telescope. They found a small little signal. Like they found some type of like pulses that were just like maybe less than a second, followed by 1 second of a pause, and then it's just repeated, like a short pulse, pause, short pulse, pause. So they're saying, oh, what could that be? And actually, they even thought that maybe this is something like related to radio communication of aliens. So the signal was referred to as LGM1, Little Green Man 1. So what was thought to be the LGM1 quite soon turned out not to be ET, but rather something natural, because they discovered that not only there, but there were more places on the sky that had the same property. That was the discovery of the first pulsar, and it was awarded a Nobel Prize like 20 years later or 15 years later, only to the supervisor, not to Jocelyn Bell. And we know today that these pulsars are compact objects, which are like objects that are very near the end of the life, and they have a strong magnetic field. I mean, a really strong magnetic field, which makes that when this object is like rotating very fast, it's emitting like double beams of like beams of accelerated particles. So what you actually are getting is that this beam, sometimes it hits into the observer, and sometimes it's off as it's rotating, like you can see here on the image, which gives rise to this on and off signal, like repeated signal. Now, the pulsars are quite interesting because they led to 3 very important discoveries. Well, the first one was the discovery of the pulsar by itself. But since the pulsars also are very, very good clocks, it turns out that you could actually measure, test Einstein's predictions of the existence of gravitational waves. And one did indeed confirm the existence of gravitational waves with the pulsars, and that led to a second Nobel Prize. But that's not the end of the story with the pulsars either, because it turns out that the first exoplanet, the first planet outside our own solar system and around another star that one found, was actually found around a pulsar. And so there was an indication of that maybe other stars could also have planets. And all that started with just the finding of one anomaly. And at the end today, we know that this image shows how shows the Doppler shift versus the orbital phase of 70 Virginis, which is a sun-like star. And what you actually see there is that you have a skewed shape of this plot, which means that you have an object that is in orbit and that has an eccentric orbit. And this famous image is the discovery of the first planet around a sun-like star. So we have managed to walk the whole way from the discovery of an anomaly that just in the radio to actually the discovery of the first exoplanets. And we have closed the circle. And that is how it can go when you're actually successful in finding a real anomaly. And we keep finding anomalies. The radio is still quite an interesting parameter space, and one discovered, for example, fast radio bursts. So fast radio bursts are something we are working with understanding now, or not we, I mean astronomers are working with it. And they are very intriguing because they are very strong, super strong pulses or bursts, and that are highly energetic, and they are usually shorter than 5 milliseconds. And up to date, we know about 500 examples of fast radio bursts. We know that whatever is producing that has a very strong magnetic field, but we don't really know what is the source of these anomalous bursts. One thinks that maybe if you have some kind of merging neutron stars, you can produce these events. However, there have also been weird type of radio bursts that have been detected. And in 2015, one discovered something that one was calling peritrons, where they had a very specific frequency and always the same length. And this happened at the Parkes telescope in Australia. And people worked on this for maybe 1 or 2 years, and they were talking about, okay, this might be an ET candidate. Maybe finally we have found the ET. Then they discovered that these signals, for whatever reason, they always happened at the same time of the day. And it happened between 12 o'clock and 1 o'clock during daytime. And it was discovered that the signal actually didn't come from the outer space, but it came from the microwave oven at the observatory. And that was the example of when not every anomaly leads to exciting scientific discovery. But at least they solved it. Another example that has been figuring very, very much in the media today is the Tabby star. So the Tabby star is a star that has showed a very brief dimming over the years. So it was discovered through citizen science. So a big citizen science project where all the citizen scientists could look at spectra, and they identified this anomalous spectrum of the Tabby star. And so what they actually saw there seemed so unusual that they wrote a paper, and they also suggested that maybe, or well, not in this paper, but in a different paper, they suggested that maybe this could come from a swarm of alien megastructures that came in front of the star. This was, of course, picked up by the media, and for 1 year we saw lots of newspapers items where they talked about an alien megastructure. Have the aliens built a big obscuring like ring of objects or something like that in front of the star? However, many astronomers who work on this are also fully aware of that young stars like this Tabby star usually have lots of dust, and just the normal dust can sometimes be very opaque. And it doesn't have to be any aliens. You can have just the natural processes that could produce the same type of dimming effect like was seen in Tabby's example. So we know that the anomaly is gone. It led to hopefully improved understanding of sun-like stars and the dust around them. And I'm sure it was to the greater benefits of astronomy to actually look into this very exciting example of an anomalous object, even if it was a natural anomalous object. So if you want to read a little bit more about how astronomical anomalies can actually push forward our scientific knowledge in even mainstream science, I suggest that you read this issue of Edge Science, where me and Dr. Marcy have written an article. So now is the question, how can searching for aliens with citizen science actually progress our understanding of anomalies? I will just drink a little. For that, I'm going to introduce you to the VASCO project, which is the Vanishing and Appearing Sources During a Century of Observations project. We are, of course, also asking ourselves, is it aliens? And we are going to look for anomalies where you can ask this specifically. This is done with a team of people. This shows the VASCO team. And so there are 4 continents involved. And we have people from Europe, US, Africa, and Asia who are all collaborating together in this citizen science project. So what is the VASCO project about? Well, it starts with an idea of that we want to look for the most extreme anomalies, and in particular, vanishing stars. So why are vanishing stars interesting? Well, because today one doesn't know of any confirmed process that could make a star totally vanish. There is a hypothesis that sometimes, maybe when a massive star is dying, instead of going bright supernova, it could directly collapse into a black hole, but nobody knows if that is correct. We call this event failed supernova events. And for the rest, if a star were just vanished, we have been hypothesizing that the best explanation would be either that you have some type of stellar engineering by super civilizations, or alternatively some new physical phenomena. So this type of events is what we really dream about finding. So when we do the VASCO project, we're comparing images of the sky from the 1950s with the sky as it looks today, and then we try to find all the things that differ. So when you do that, you're not only going to find vanishing stars if you're lucky. You might also find other type of objects. You might find, I told you before about active galactic nuclei and quasars, and you might find some such that are varying on a long term over 70 years, very slowly. Maybe it will dim and then it will get brighter again. You might also find cataclysmic variables, or like stars that are having very strong variability. But usually they don't have 70 years of time scale, but we talk more about hours or months, or at maximum maybe some year. You might also find things that flared up, like some type of transient, we call them transients, that, well, we call all these transients, but you might find an object that flared up in the 50s and that now is gone. And maybe you're lucky, you can find a communication laser also. And maybe you can find other type of phenomena, natural or unnatural. So this is what we are interested in, and astronomical anomalies, explainable or unexplainable, natural or unnatural, but hopefully we could find some vanishing star. So as I mentioned, the first example are failed supernova. Here's a failed supernova candidate, and I'm not sure if the candidate hasn't failed already by now. This is not ours. Another thing that I also mentioned are these like quasars and active galactic nuclei that might have some type of long-term variability. These are particularly interesting because they are challenging all the models we have of how this light is produced. So in 2020, we published our first paper, and we identified 150,000 of candidates that have to be looked through by eye, one by one. In the first paper, I challenged myself and I looked through 24,000 candidates alone. That's 2.5 times as many images. It was 3 months of chocolate, tea, and I lost 1 dioptry in sight. It was tormenting, but necessary to do. So here's an example of the kind of stuff we found. You see here one star-looking thing. In the 1950s, you see it in the red band, you don't see it in the blue band. Here is the 2000 and 2015, and that thing was only seen once in the 50s. Another such example here, you actually see something in the red band, you see it again in the blue band, you see it in one more band in the 80s, and then it vanishes. So it's one of our better candidates. And we found 100 of these when we looked through these 23,000, well, the 15% of the 150,000 candidates. So 100 of these, it was a lot of work. And they were all kind of point sources, so it looks like a star. They had the same brightness profiles as the stars, but maybe these are not really vanishing stars, but rather some type of transients that are maybe very, very short. And or very red, but I'm going to guess on very short. Maybe they were only there for a few minutes and then they vanished again. We could exclude very strongly variable stars. We could exclude supernovae, at least like at low redshifts. These are no solar system objects, and based on the brightness profiles, they are unlikely to be plate flows, even if you cannot completely exclude it. And our best guess is that some type of dwarf stars might have had some kind of flare and that we caught it in the bright moment, or that you actually catch the afterglow of one of these fast radio bursts or a gamma ray burst, as I mentioned before, which are like super energetic events that are lasting just a few minutes and then they are vanished from the sky. They are also very enigmatic, so it's cool if I find something there as well. Sorry. That's so how have we decided to analyze all the other candidates through a citizen science project? So this is the team who have built the citizen science project, and it's a cross-disciplinary effort of machine learning scientists, image analysis researchers, game researchers, and astronomers. So the goal has been to build this citizen science project that is gamified, and where each citizen scientist can look at 2 images and tell us whether a star has vanished or not. And it also has a machine learning solution. However, they are still working on it. So let's see when it will be finished, where in principle, instead of getting, right now you have a random image. Let's say that you go to the website and you get a random image where you can compare the 2 images. When the machine learning solution also is going to be like actively, right now it's in training, but when it's also going to be active, then the what's called the algorithm is going to not give you things by random, but give you the most interesting candidates. So I look forward to when this effort will be finished in development. So here I have the first what's called a splash screen of how it looks. I was thinking of showing you actually the citizen science project itself. However, I have a PDF here, and I think it's going to be quite complicated to jump between PDF and the first page. So what I will do is that I will send you all the link so that you can look at it over the chat. So we have a web page both in French and in English. So each user can go there and compare candidates. And a user can also go and inspect the images in detail if the user clicks on a particular inspect button. And if any anomaly that has nothing to do with vanishing stars is found, the user is also welcome to point this out. Yes, so this is what you actually see once you click yourself into the system. You're asked to compare the central objects in the 1950s with the same field as it looks today. And here is this inspect page. Here you have the matching. You can also match the images and overlap them and see how well they are matching, and if there is something missing or not. It can help to, you can rotate them, you can make them change them in size, because you have all these differences that might act out just due to instrumentation. And this we do in collaboration with actually several institutes and amateur astronomy associations, in particular in Nigeria, in Cameroon, and in Algeria. For example, these images are taken from the African Astronomical Association and the Serious Astronomy Associations meetings, where they are teaching children in high schools how to use VASCO to look for aliens and other astronomical anomalies. So they're actually doing entire workshops in looking for anomalies, and where they can learn about ET, they can learn about various astronomical events, about time domain astronomy, and it seems like the children really find it fun. So they also arrange competitions, who finds most anomalies, and so on. So much of these activities are led by Kaola Lagune, that is also leading a separate initiative called VASCO for Kids. That is like super cool. So even if we don't find any aliens, I hope that we will inspire many children to look for anomalies and aliens in the future. So these are the stats from the 20th of October. I've been also asking for the latest stats, but I haven't received them because there are some complications. The person who I asked is currently ill and didn't have time, since I just sent a request yesterday. But from what I can see, it has increased from 221,000 classifications to around 250,000. When we had the slightly smaller sample, we had around 3,900 vanishing stars, or candidates of vanishing stars that the citizen scientists had marked. Then they also found 6,000 other interesting objects for us to look through, and they had commented on 2,400 cases that are particularly interesting. And we are actually now already going through the most interesting candidates, like these ones and those, with the research team in VASCO, to try to only select the most interesting of the candidates. So this is an example of something we found before the Citizen Science Project, but that I hope we can find more of. So we published a paper in Scientific Reports that belongs to the Nature journals, where we found 9 stars marked in the green circles. In these green circles, you can see these 9 point-like objects that were seen in an image in the 1950s, and it vanished like within half an hour. So they all appeared within half an hour and all vanished within half an hour. So we had to do like lots of tests. There's absolutely no astronomical explanation for these 9 simultaneous transients, as we refer to them. There's nothing of the known astronomical that can produce this. So we've also been testing a lot of instrumental explanations without identifying a particular one. So we proposed that maybe this is some type of contamination. Maybe it could come, for example, from nuclear fallout from atomic bomb tests. However, there are no official atomic bomb tests in the United States exactly that date when the image was taken, or even that year. And the other alternative that we also mentioned is that maybe this could actually have an explanation in that you have some type of orbital debris I mean, like orbital debris, like destroyed satellites or space trash that could produce glints. Because today, if this image would have been taken today, there would be nothing weird about it, because we have millions and millions of debris pieces at high altitude. But this image is taken from 7 years before the first satellite was launched. And this is where we have discussed that we need to develop the citizen science project more, because these photographic plate surveys that we use, these old plates that were exposed before we had any human activity in space, they are actually really fantastic to look for alien artifacts near our Earth, because of the cleanliness of the sky. And for example, on low orbit, you can find some unusual streaks, maybe. And here's an example of an unusual streak that we still don't understand, that we found in the data, it's from the 50s. But if you are on high orbit, for example, the geosynchronous orbits, you could have multiple transients, like the case we showed before, as a signature of artificial objects that shouldn't be there. Here I show you like one example of something where you have 2 stars that are there in 1950s and aren't there. If you have a rotating dish, you could actually see 3 stars in one image. Here you see it in an image from the 1950s. And if you're really lucky, now there's a small error here. And I think it's because I have, it should be equal to or larger than 4, not larger than 4, just equal to or larger than 4. And what you would find then is that you could actually find several of these transients along a line. And you only need 4 of them in order to say that this is not random in an image. Because if you have an image that is, let's say it's 10 arc minutes by 10 arc minutes in size, and if you have maybe 10 stars, 10 transients there that all randomly appears at the same time or vanishes, then you need that 4 of them are aligned in a line in order to say that this is not random. They are actually following a line. So we have, through the Citizen Science Project and through the automated methods we have worked on together with the Spanish Observatory, we have automatically identified cases of simultaneous transients and try to look for if we see any case where you have 4 transients along a line, in order to confirm the idea of that you have a space trash in a geosynchronous orbit. Funnily, we do find actually several such examples. Here we have, these ones are falling perfectly on a line. Here we have 6 stars, and you see them here in one image, and they are not there half an hour later. It's not a strong evidence, because here statistics is going to act either in your favor or against your favor, and some things are really difficult to get a good estimate of. Here's another example where you see 5 objects all very closely to each other. This is a 4 sigma event if you do the statistics. However, you can still ask yourself, if you look through enough of many cases, maybe you will find that. And that's why we can't really claim that it's conclusive evidence, even if we have something in the favor of that it can be falling upon a line. So in the end, the only thing that will tell us if this effect is real is going to the original plate collection, using a microscope and looking if these stars are actually looking like real stars, also under the microscope. The problem is that we do not get access. We haven't gotten direct access yet, and that's because they treat the plates as gold, and the external people simply cannot go there. Someone else might look for you, but maybe you don't want to just hear someone saying, yes, this is real, this is not real. You actually want to look at it and analyze the cases very carefully. So this is where we are right now. And in the Citizen Science Project, we hope to soon implement more functions to look for this type of events. So summary and outlook is that with the VASCO project, we're looking for vanishing stars, unusual transients, and you can test both conventional astrophysics questions, and you can also test exotic questions related to anomalies or SETI. And there seemed to be an interesting space for us to explore when it comes to the searches for multiple transients in all photographic plate surveys. Because maybe they are caused by the GEOs, or maybe they are caused by some other type of events where multiple objects appear simultaneously on the sky and vanish simultaneously. And regardless of if it's the first or the second option, I think it would be extremely fascinating if we just know that these events are real. And I hope that with this citizen science project, we can actually uncover more secrets of the universe, and we can do this together with the students in Africa that work with us, and that we can do all this exploratory journey together. And researchers that are interested in collaborating with us are welcome to contact me. Thank you.
All right. Thank you for your talk. It was nice to get a little bit more detail on the citizen science project, because we've been on the stage before discussing it, but it was nice to get into it even more. We do have a couple of questions in the Q&A, which I'll get to in a moment. I just want to remind, only one question now. I just want to remind SSE members that they are invited to raise their hand and come up on stage to ask their questions directly. Or you can put it in the Q&A box, and then also, you can upvote your questions in that box as well. So I'm going to go ahead and end your presentation. So hold on. There we go. Now it's just us. All right.
Unfortunately, my voice is the COVID.
It's okay. We appreciate you being here. All right. So this is from Robert Schutz. He asks, what kind of machine intelligence techniques are being used?
For anomaly detection specifically, and the person that can tell you exactly all about the machine learning techniques is Christian Pelkmans, and if you want, I can get you in touch with him. Right now, the results that we're analyzing are coming from the classical projects where we haven't used any of the machine learning results yet, because I'm still waiting for the machine learning bits to be completed.
Okay. Now, about how long has this project been going on, and about how much longer do you think it will be going on for?
So I'm almost out of funding. I'm not sure if that gives an indirect limit or no. So we started it. I did my first search for vanishing stars in 2016 in my third or fourth year as a PhD student. So at that time, I did it completely manually myself with two bachelor students. We looked through lots of stars, and we found a candidate. And then there was the problem that we had only explored 1% of the database. So then it took some more time until 2018. We had a workshop together with Dr. Christian Pelkmans and more people. Also some people from the Breakthrough Listen were there when we decided, okay, let's do this on a big scale. We have to automate it, and we have to solve all these big data challenges, because the big data challenges come with 80 terabytes of data, image data. So we started thinking about, let's do a citizen science project. We started working on the citizen science project, and we started there. And that was like 1 or 2 years of setting up just the infrastructure. Then I got in touch with the Spanish Virtual Observatory in December 2019 with Professor Enrique Solano, and there he could automate the methods to search for these transients. And right now, like 2 or 3 years after, he has submitted the paper, because it was so difficult and so enormous amount of work. And this is just to identify the candidates, and with the citizen science project, we have now collected all the data we need to do a preliminary data analysis. So I think we will have the first phase might be completed by the end of the year, but we will have more challenges with like interpreting everything, observational follow-up, and that will take another 5 years. So that's how it looks.
I'm wondering, do you think we could bring up, I think we'll be able to do this, bring up the project, the link that you shared, and can you show us what it looks like to do a trial?
Yes. So let me open it. So I have to share my screen somehow.
Cross your fingers.
Share screen. Okay. So I will do this stuff. Does people see the website?
Yeah, I see it.
So this, when you come to the website, you come to a splash screen, and then you can click here and say, okay, so let me pick a more fun example. This one is boring. We have seen this several times, so I will just do like randomly say the object is there. So now you are going to find this a case when someone asks you to focus on the central object in the left image. In this case, it's this one. Has the star vanished, or which option fits the best? Well, in this case, nothing has vanished because this is the typical artifact that you can find when you have a very bright star. So no, there's nothing fun here, but one can have some fun with rotating the images, and we see that here nothing has vanished. The object is still there. So you submit the case, and you hope for that the next case will be somehow more fun. Right now, it's the random mission generator, but once the AI will be finally developed, it will not be random anymore. So here we have another case. Is there something interesting in this image? I'm sad to say that I don't see anything interesting, but maybe I will go to the inspect just for fun and see if there might be something else. I look here and I still don't see too much of fun stuff, because you can look like in different bands. In the blue band, in the red band, here are all these images from the 50s, 80s, and these are from the Pan-STARRS, that's like 2015. And let's say I see Santa Claus, then I can write something here and I can submit it. Anyway, I go back and I say, not a very fun mission. And I do it again, and in this way I can play with the with the case, and I can also do play with the contrast here. I think it's something happened here. Yes, you need to click on that thing first. Yeah, well, there's a certain gamification, so we also have a tutorial where they teach what to look for.
Okay.
So
I didn't realize there was a tutorial. That would be helpful for me, because I'm still deer in the headlights looking at the project.
Well, now I need to stop sharing.
I can do that for you.
Okay, perfect.
Okay, awesome. All right, and that is open to anybody who wants to participate, right?
Yes, absolutely. Everyone can participate.
Excellent, excellent. All right, we have one more question from Robert. He wants to know, has Halton's ARP quasars observations been explained?
I would say that they have been put under the carpet because people got tired of arguing about them, and there was not a super consensus. So since there was no scientific consensus, there became a social consensus on saying that it's probably just what's called projections, chance projections.
Okay.
So
sounds unfortunate.
Yeah.
Okay, well, that's it for our questions. So I think we'll go ahead and stop here and get prepared for the next session. Thank you again for joining us today and for your talk.